Hi, my name is Sean Curtin, and this is my project on functions of two variables and surfaces. The world we live in is deeply rooted in mathematics. As our technology continues to evolve, we uncover new ways in which math reveals the underlying structure of our universe. Mathematics has sparked many of our technological advancements, revealing patterns in engineering and nature. From natural formations to man-made complex machines, math has helped us model, analyze, and improve the world around us. One of the most important evolutions in mathematical thinking has been multivariable calculus, which started to develop during the Renaissance. Since then, it has been an essential building block to some of the most important inventions and technologies we've made so far. Multivariable calculus is so powerful because it extends math into the world of 3 dimensions and beyond. By considering more than just one variable at a time, we unlock a new way to interpret real-world situations. A function of two variables is what the name alludes to, a mathematical function in multivariable calculus that uses two variables, typically labeled x and y, to give a single output value, usually referred to as z. The basic idea is similar to single variable functions, but instead of mapping input to output on a curve, we map input pairs to points in a 3D space, which creates surfaces. When two surfaces intersect, the resulting intersection often forms a curve or region in space, which can reveal critical information about their behavior. It can also define a curve or region. This reveals valuable data that can be useful in a multitude of real-world applications. Functions of two variables are valuable in many sectors such as engineering, medicine, and other STEM topics such as environmental science and weather. This graph here is the most basic example of a function of two variables. It is z equals x plus y. This extends the familiar idea of functions like f of x equals y into 3 dimensions, but with the addition of z, which brings the function into the 3rd dimension. When modeled in 3D, a function like z equals x plus y creates a simple linear surface, a plane that rises evenly as either variable increases. The format of these functions, written as z equals f of x and y, introduces an extra input and output dimension, moving from the flat world of 2D curves into the richer world of 3D surfaces. Using familiar concepts from single variable functions like squaring, exponentials, and subtraction can help build more interesting and complex surfaces. Consider the following examples to see how different operations affect the resulting surface. This is a 3D surface plot of z equals x squared plus y squared, and it creates a paraboloid, which creates a smooth upward-facing concave bowl surface. The next 3D surface plot is z equals x squared minus y squared. This results in a saddle shape which curves up on the x extremes and down in the y extremes. And then the final of the simple 3D surface plots, z equals e to the negative x squared plus y squared, which produces a spike or a bell shape, often called a Gaussian surface. The domain of a function defines the set of value coordinates, which essentially outlines the region where the function is applicable. In practice, visually, it acts as a fencing or a boundary where the function is in play. For example, imagine a wildlife researcher studying mountain goats is given a 3D elevation model of a mountain that the goats inhabit. This map shows where the goats live, which is between 1,500 meters above sea level and 4,000 meters. The domain of this function must be limited to a specific altitude range. If the domain is misdefined, it could lead to inaccurate data collection and costly errors. In a graph, the domain might be visualized by highlighting the region, such as a red band, illustrated as seen here, showing where the goats live. This naturally introduces the next key concept, level curves. Level curves are the cross-section lines of a surface at a constant value of z. A real-world example of this would be altitude lines on a topography map, which indicate the heights of different coordinates. In this goat habitat scenario, level curves show regions between 1,500 and 4,000 meters, helping the researchers know where the safe zones are very easily from a top-down perspective. These contour lines help immensely in planning navigation in rugged, tricky terrain. In mathematics, every new idea is built on what came before it. Functions of two variables and surfaces are the stepping stones to other, more advanced and powerful techniques. One of the essential next steps is the concept of partial derivatives. As the name suggests, a partial derivative is measured for how it changes with respect to one variable at a time while keeping the other one fixed. This leads to gradients, which use partial derivatives and give us a vector that points in the direction of the greatest increase. The gradient vector's magnitude tells us how steep this increase is. They are incredibly useful for optimization problems and appear throughout physics, engineering, and data science. Some of the most advanced machines that humanity has created have relied on these mathematical concepts. Especially so have been modes of transportation. Whether it's planes, trains, rockets, or cars, all of them use the physics of liquids and air to optimize their efficiency and performance. Controlling airflow has led to some of our most significant technological advancements. A key part of this progress was the National Advisory Committee for Aeronautics, or NACA, the predecessor to NASA, which developed a series of airfoils that were tested starting in the late 1920s and into the 1930s. NACA helped lay the groundwork for many different uses of airfoils today, whether it's airplane wings, helicopter blades, car spoilers, bullet train noses, wings of rockets, motorcycle winglets, and much more. Below is a graph of a NACA 2412, which is a common airfoil used in airplanes. Its shape is defined by a set of mathematical equations that help generate lift efficiently. This is another usage of functions of two variables that are very relevant to our everyday lives, whether it's the curve of an airplane wing cutting through the air or a topographical map of a mountain. Functions of two variables are behind the surfaces that shape the world we inhabit. Overall, learning about the topic of functions of two variables and surfaces is extremely helpful for understanding the visual three-dimensional world we live in. All of the textures of all of the surfaces that we touch have these concepts woven into them, whether it's designed by nature or man-made. As we venture forward into new technologies and unforeseen scientific challenges, understanding these guiding principles of the mathematics of surfaces will be crucial. Thank you for watching the accompanying video to my Calculus 3 project about functions of two variables and surfaces.